Good time, everyone. Today I'll be presenting research on computational optical distortion correction for head-mounted displays. This work was conducted by, I hope I spelled the names correctly, but by Changku San, Xiaoting Gu, Peng Wang, and Baoshang Zhang, and published in Optic International Journal for Light and Electron Optics. Before we begin, uh, I want to first introduce myself. That I'm Mohammadjavad Maheronnaghsh. I want to present some works on augmented reality systems, and this is a paper named Computational Optical Distortion Correction based on local polynomial by inverse model. Okay, so this presentation focuses on how we can correct complex distortion patterns that occur in augmented reality head-mounted displays using an inverse mathematical model. Okay, so here we don't have anything. Oh yeah, we have actually HMD here, head-mounted displays. I would say it's actually a wearable device with small displays positioned in front of the user's eyes, used in VR or AR applications. I mean, virtual reality or augmented reality applications. Okay, so we go to the problem. The optical distortions in HMDs or head-mounted displays. Okay, let's start with the problem. In optical systems, particularly HMDs, used for augmented reality, we encounter a significant challenge: optical distortion. This distortion warps and deforms the images we are trying to project, making the viewing experience uncomfortable and reducing the accuracy of information recognition. So this paper mostly focuses on the geometrical distortions. Actually, I would clarify it more in the rest of the presentation. The challenge becomes especially severe in modern HMDs because they use wide-angle optics with off-axis configurations to achieve large fields of view while keeping the device compact and lightweight. So this creates highly complex and non-symmetric distortion patterns that are very difficult to correct. Looking at the characteristics, we can see that several features. Uh, I mean, it's non-uniform and asymmetric across the viewing areas. It combines radial distortions, where warping increases with distance from the optical center, and tangential distortion, which is actually it's maybe I can say it's perpendicular to the radial distortion actually. And you can also get unconventional bow-shaped warping. And most importantly, this distortion is most pronounced at the edge of the field of view. I say, oh, and I have to actually clarify something here. The FOV term here that we have, the FOV or field of view, it's actually the extent of the observable area visible through the device, measured in degrees. For example, 40 degrees by 30 degrees, something like that. Here we have, let me see what I have here to say. Oh, we have off-axis word here. It actually, when we say off-axis optical system, we mean optical configuration where light travels at angles rather than straight through lens centers, and creating asymmetric distortion, radial distortion. So I mean, not necessarily radial, I mean asymmetric distortion. And we have another word, radial distortion. Let me find it. It's somewhere here. I don't know why am I missing it. Yeah, But I mentioned radial distortions before, and it actually means image warping that increases with distance from the optical center. And the other thing is tangential distortion, which is perpendicular warping, often from misaligned optical elements. And yeah, that's it. So let's go to the proposed solution that we have here, which is actually the inverse modeling. And it is combining reverse spatial transformation with pixel filling achieves efficient correction. So how do we solve this problem? The researchers actually propose using an inverse model approach that combines reverse spatial transformation with pixel filling to achieve efficient correction. And the key innovation is in how they think about the problem instead of trying to predict where each distorted pixel should go, which requires actually complex mathematical inversions. They work backwards. They ask, for each pixel in the output image I want to create, where should I get the correct color from in the input image? And this direct mapping from distorted coordinates to ideal coordinates eliminates actually the need for solving complicated inverse functions. And the method uses a local approach instead of trying to fit one equation to the entire viewing area. They are dividing the field of view into multiple regions or zones, and each zone gets its own dedicated polynomial function that describes the distortion in that specific area. And this is crucial because distortion varies significantly across the field of view. And finally, they use a region overlap technique by making adjacent zones slightly overlap and blending the corrections in the overlap areas. They eliminate actually the visible boundaries between corrected regions and resulting in a seamless final image. And yeah, I think maybe I can just say very fast that by inverse model, we mean because we are mentioning the inverse modeling here, and by inverse modeling we mean a mathematical approach working backwards from desired output to required input, rather than forward. Rather than forward approach. And yeah, I think and I should also mention what do I mean by polynomial function. It's actually a mathematical equation using powers of variables like x to the power of 2 plus something, and it models curved distortion patterns. Okay, so and we also mentioned a local things in local approach here. So I should also say that when we say local, we mean the local approach uses different parameters for different regions or zones, but global uses one set for entire image. Okay, so the correction algorithm, let me walk you through how the algorithm actually works. There are three main steps. First, we estimate the parameters. We start with a standard test pattern, a perfect grid, and display it through the optical system, and we capture what comes out with the camera. By comparing the ideal grid positions with actually where they actually appear in the distorted image, we calculate the polynomial coefficients describing the distortion in each region locally. Secondly, we generate a pre-distorted image. This might sound maybe counterintuitive, but we intentionally warp a normal image in the opposite direction of the polynomial distortion. And we do this by transforming pixel coordinates and using interpolation to calculate color values. And thirdly, we display and compensate actually when we project this pre-warped image through the optical system, the system's distortion and the pre-distortion cancel each other out, and the viewer sees an undistorted image. And if you look into this pseudocode, you can see the two main loops. The first divides the field of view into m regions and fits a polynomial to each, solving for coefficients using least square optimization. And the second loop processes each output pixel. For every pixel position in our output, we use our polynomial function to map backwards to find where in the input image we should sample from. Then we use bilinear interpolation to calculate the color value from 4 neighboring pixels. And and I use this pseudocode from standard image processing reference. Actually, uh, the Gonzalez and Woods digital image processing. And yeah. So let me go to the next slide, which is bilinear interpolation and grayscale processing. Now let me explain in detail how bilinear interpolation works and what we mean by gray or grayscale processing, because this is a crucial part of the correction algorithm. Bilinear interpolation happens in 3 steps. First, we map our output pixel coordinates to input coordinates. And when we have an output pixel at position u and v, our polynomial function maps it to an input position x prime and y prime. And here's the key. X prime and y prime are usually not integers. They might be something like 5.3 and 7.8, but our digital image only has pixels and integer positions. So secondly, we find the 4 neighbors. We locate the 4 surrounding pixels at integer coordinates using floor and ceiling functions. We find the 4 corners of the square containing our non-integer position. So in our previous example, 5.3 and 7.8, it's going to be 5, 7, 6, 7, 5, 8, and 6, 8. And finally, in the step 3, we perform weighted average, which is we actually compute a weighted average, and the formula is shown here. The fractional parts dx and dy represent how far we are from the lower left corner. If we are very close to the 1 pixel, it gets more weight. If we are in the center, all of the 4 pixels contribute roughly equally, and the variables G1 to G4 represent the grade levels or color values of those 4 pixels. And now let's answer this important question. What do we mean by gray or grade level? In digital images, this is simply the pixel intensity value. For grayscale images, it's basically a number from 0 to 255 for 8-bit integers. So 0 is black and 255 is white. For color images, we have 3 channels, RGB, red, green, and blue, and we apply the same interpolation formula separately to each channel. And what do we need? Why do we need interpolation? Because when we transform coordinates, they rarely align perfectly with the pixel grids. So we need to estimate intensity values at non-integer position. And yeah, I think if I want to say in other words, the grayscale, the pixel intensity value typically it's actually 0 to 255, but the term gray is used even for color images where we process RGB channels separately. So it's not actually gray, but we are separately processing the RGB actually. And I think we can actually go to the next slide. So based on my understanding from the paper, actually I can say we can now actually go to the results and how this method compares to the baseline approaches. They have achieved an impressive 98.6% reduction in distortion error, and they compared their method against 2 main baselines: the forward model using pixel carryover, which is basically maybe let me think, how can I describe it? Mm, actually, uh, I can say you go over each input pixel and determine where it should be placed in the output, and the problem is serration artifacts. Uh, and the second one is the global model that uses a single polynomial for the entire field of view. This approach actually cannot model local deformations effectively when distortion varies across the field of view, and actually which it does in off-axis system. So a global method simply can't capture all the local variation. uh okay, so, and looking at the quantitative results, I can say before correction, the maximum error was 283.5 pixels with an RMS error of uh, actually 112.2 pixels, giving a relative error of 187.8%. That's almost double the ideal value. And after applying the correction, the maximum error dropped to just 1.99 pixels, where with an RMS of only 0.83 pixels. So a relative error of just 0.68%. And and they also compare different polynomial orders actually. So the optimal one is the third one actually. And yeah, so I think I can basically go to the key findings here. Let me highlight the key findings that validate this approach. First, the inverse model clearly outperforms the forward model. The forward model with pixel carryover creates edge artifacts and pixel duplications issues. And the reverse mapping approach prevents these problems because it pre-processes the output systematically, ensuring every pixel is handled exactly once with no gaps or overlaps. Secondly, the overlapping region method proved essential. Without overlap between adjacent zones, you get visible seam lines, actually abrupt changes at zone boundaries. So the blending in overlap areas creates seamless transitions. And thirdly, the cubic polynomial that's third order with 25 zones was optimal. This configuration achieved the best precision without introducing seam lines or requiring excessive computation. And yeah, that's it. We are almost done with this presentation. Let me conclude by summarizing the main contributions. The reverse model with regional polynomials successfully handles asymmetric distortion in off-axis optical systems. This is significant because traditional methods assume symmetric distortion, which doesn't match reality in modern HMDs or head-mounted displays. First, direct coordinate mapping eliminates. Oh, sorry. Okay. First, I can say direct coordinate mapping eliminates complex mathematical inversions. You don't need to algebraically solve for inverse functions, which can be difficult or impossible for high order polynomials. Secondly, the filling strategy prevents pixel gaps and duplicates by processing from output to input. Um, and thirdly, the regional polynomial approach handles non-uniform distortion effectively, since different field of view parts can have very different characteristics. And fourth, zone overlap ensures continuous transitions between regions. And fifth and finally, the chief subpixel accuracy less than 0.9 pixels mean error, meeting demanding precision standards for augmented reality applications where accurate alignment between virtual and real content is critical. And this method is applicable to wide-angle off-axis optical systems in AR applications, making it valuable for next-generation head-mounted displays. And yeah, that's it. I mean, I think I'm done with everything here. These were my understandings from this paper. Thank you for your attention. I'm happy to take any questions. Yeah.